Hi there, I'm David, and today we want to talk to you a little bit about the background of one of the tests we do here in the lab. It's a tension test for concrete. Now, tension in concrete is kind of tricky because tension strength in concrete is kind of small. Today we're going to talk about an indirect method of measuring tension in concrete, ASTM C78, the beam in third point bending test. Now you've seen our fun little foam beam in the past, and we know that if we put a load on this beam, it'll flex down, and look, it's wider at the bottom, smaller at the top, tension in the bottom, compression in the top. Concrete's weaker in tension, stronger in compression. It's going to fail first in tension. So this is essentially a tension test, really classified as an indirect tension test. A direct tension test would be tension in this direction. Whoever designed this test for the first time was really clever. There's this very big, massive steel seating beam that goes on top of a concrete beam. So this beam's made out of concrete. It's what we're going to be testing. Sits on simple supports. So the load cell from the load machine comes down and applies the load, and this load spreader spreads it out so we get P over 2 at third points on the beam. Now, what we're going to want to do is we're going to use the stress and bending equation. This is derived in many places, found in statics books, engineering textbooks, all over the place. So I'm not going to bother to derive this. This is very well known. We're going to use this equation. We're going to need moment at a cross section of the beam. We're going to need C, which is a half height of our rectangular section beam. We're going to need the moment of inertia. So we've got two geometric properties. We've got one property from the loading. We're going to use that to calculate stress and bending. So back here, this is very common. This is our shear diagram. We integrate our load, and it gives us our shear diagram. We integrate our shear, and that gives us our moment diagram. Now let me explain why this is so incredibly clever when they set this up. Note that in the shear diagram, there's no shear in the middle third of the beam at all. The way this is set up, it eliminates shear in the middle third. And note that the moment is maximum in the middle third of the beam using this boundary condition setup. So isn't that clever? We're going to measure the stress due to the moment, the pure bending stress in the beam, and use that to calculate our value. And no shear in that same region. So this boundary condition, very clever way to set it up. Let's move back over here. For a rectangular section, we have the width and the height of the beam. Moment of inertia, very commonly found, not going to drive this, very commonly found in many textbooks, reference guides, found many places. Rectangular section, 1/12 BH cubed. Distance to the outside fiber from the centroid, C, that's C, the distance to the outside fiber, H over 2 because it's symmetric. So obviously the distance from the center to the outside is H over 2. We're just going to plug that in. Very simple. We're going to plug in moment, our maximum moment in the center third of the beam, PL over 6. That comes from our force, stress, shear, and moment diagram. We plug that in. That's M. C, H over 2, H over 2, H over 2. We plug that in. Moment of inertia, 1/12 BH cubed. We plug that in. And then we simplify that, and we get the stress in the outside fiber of the beam, PL over BH squared. That's merely algebraically simplifying this substitution. Now if we look in C78, ASTM C78, the specification for the beam and third point bending test, you'll see the PL over BH squared expression. You'll see this algebraic expression, but it won't be referred to as stress. It is stress. It's the stress in the outside fiber. It'll be referred to as the modulus of rupture. Now that's a little confusing. Why on earth did the committee decide to do that? Well, they decided that because they decided from the theory of elasticity that this may not be the perfect expression for stress in the outside fiber. It may be that the stress comes down and then tapers off a little bit towards the edge. So they decided to name this the modulus of rupture to distinguish it from confusion of being the direct tension test in the outside fiber. That's it. This is a pretty simple test to understand. You have to understand how the boundary condition works to simplify the stress state. Once you know the stress state, plug it into the stress and bending equation, simplify it algebraically, get what is known as homologous rupture in ASTM C78. That's pretty much it. I'm David here from the Intelligent Concrete Labs in beautiful Elbert, Colorado. Thanks for looking in. Don't forget to like, to comment,
and subscribe.
and what else? Go concrete.
Beat asphalt.